Okay, so we had started looking at the two-dimensional heteronuclear correlation experiments. We had done some part of it in the previous lecture. So we will go further from there. We'll start from there from where we left. Okay, so this we discussed these pulse sequences, heteronuclear COSY direct detection, one experiment which is simple COSY type, except that you have X nucleus there. Two channels are separately required. One channel on H, another one is for X. So typically the spectrum will look like this. So this is what we had done this already. Then indirect detection scheme, here you detect the proton instead of the X nucleus. And the spectral features are very similar to that, except that you have a better sensitivity because you are detecting the proton. So it is the signal to noise ratio is proportional to the gamma h to the power 3/2. In the previous case, it was gamma x to the power 3/2. So now then we extended further, say, okay, we will do decoupling. In the previous cases, we could not decouple the carbon-13 from the protons. So this proton-carbon coupling could not be removed. So now we can actually decouple by doing the refocusing experiment. So we refocus the after the initial transfer. So we have this refocusing period here from here to here. So that is after that one can actually decouple the X nucleus from proton, and that will result in experiment with the spectral features which are like this. We still have the coupling along the F1 dimension, but the coupling along the F2 dimension is removed because we are decoupling in the F2 dimension, the broadband decoupling. So we had done that. And then similarly, you can do the other way, direct detection. You heteronuclear, the same experiment, but now instead of the indirect detection, you do a direct detection here. You observe the X nucleus and decouple the protons. So here what happens along the F1 dimension, we have the proton frequencies. F1 dimension are the proton frequency, F2 dimension we have the X frequencies, and the peak pattern will remain the same. Along the F1 dimension, the coupling will be there, and F2 dimension the coupling is not there because we have decoupled it. And here the sensitivity is proportional to gamma x to the power 3/2. So we had done up till this last time. So we will continue from there to improve upon these pulse sequences, and let us see what is the next thing to do. So we want to gain the benefits of proton detection and proton excitation. So therefore, we want to get a maximum signal to noise ratio, and that comes from this particular modification, which is called as the heteronuclear single quantum coherence or heteronuclear single quantum spectroscopy, correlation spectroscopy, whatever. So we call it as HSQC. So this has the following pulse sequence. You see here how the experiment works. So this portion is the initial transfer step, which is the inept transfer step from proton to the X nucleus. The tau is to be adjusted as to 1/4J. So the total 2 tau is 1/2J. The magnetization is transferred to the X nucleus at 0.2. And then during the period from here to here, so therefore the single quantum coherence of X nucleus evolves, is the chemical shift will evolve, but the coupling constant from proton to X is removed because we are putting a 180-degree pulse in the middle of the proton channel. So if you have seen earlier that if you apply a 180 pulse on only one of the two nuclei, then it leads to kind of a decoupling. So therefore, the proton X coupling is effectively removed at this point here at 3. So therefore, there is no evolution under the proton coupling. And then after that, so the magnetization is transferred back to the proton here, and that is antiphase with respect to the proton. So therefore, what we do it from this point, we refocus here just as we did in the previous cases. And I will show the actual product operator calculation in the next slides. So you refocus it here, and then you collect the FID and decouple using the GARP. This GARP is a decoupling scheme. So at these different time points, so what will be the density operator, product operator calculation one can do? Now this GARP stands for Globally Optimized Alternating Phase Rectangular Pulse. This is a complex pulse sequence here itself, which will have several pulses. It has some large number of pulses with varying amplitudes and phases and things like that. So we will not go into that details here. So this is a kind of a module which is available. So you can go into the spectrometer, you can simply say GARP, GARP will come. So there are certain things like that. There is a MLEF 17, there is a GARP there, then there are also some other pulse sequences of that type. which are there to decouple broadband decoupling. So the spectrum will look like this. So in this situation, now you see there is no coupling along the F1 dimension and there is no coupling along the F2 dimension also, because you are decoupling here. F1 dimension you are decoupling because of this 180 pulse. F2 dimension you are decoupling with the broadband pulse, broadband decoupling. Therefore, in this kind of a spectrum, now the proton will appear along the F2 dimension, X will appear along the F1 dimension, and there will be no fine structure at all because you have decoupled both along the both axes. So this is, let's look at the product operators here. The relevant product operator terms. Rho1 is Hz. This is the Z magnetization of proton, because we start with the proton. We start with the proton. Rho2 is at this point. After the inept transfer from the proton to the X nucleus, that is Rho2. After the inept transfer, you will get 2Hz The magnetization has now come to X nucleus, and it is antiphase with respect to the proton. You can see that is 2Hz. Now, then between the time points 2 and 3, what all things will happen? X chemical shift evolves for the period T1, because the magnetization is all on the X, is on X. Therefore, it is the X chemical shift. X chemical shift evolves for the period T1. The proton chemical shifts are refocused. There is a 180 pulse in the middle of this T1 period. Therefore, chemical shifts of the protons do not appear. Then you might say, where do the proton chemical shifts come? In case the proton X nucleus, there is not 100% labeling. If there are, suppose there are protons attached to carbon 12 and not carbon 13. So those ones will continue to be there. They will be present here. They will go through like this, and they are getting refocused all the time. They will be refocused here, and refocused here. That is why we have written in this style here that proton chemical shifts are refocused. And then for those protons which are attached to carbon 13, they go through the X channel. Okay, this product operator description what we have written is for those which are attached to the carbon 13 or the N15 or whatever, the X couple. And in this situation, this proton chemical refocusing means it is a decoupling scheme. The proton excess coupling is removed. During this period, excess coupling is removed. Therefore, at time point 3, the magnetization still remains on X, but it is antiphase with respect to proton, because it has not evolved under the proton X coupling. Therefore, it remains as 2Hz. However, it has acquired some time-dependent coefficient FT1, and this comes from the chemical shift evolution. Because during the T1 period, chemical shifts are evolving. So here you see the chemical shifts are evolving during the period. Therefore, a function Ft1, which represents some amplitude of the chemical amplitude evolution, that will remain. So that we write here as Ft1. And ρ4, what happens at ρ4? ρ4 is immediately after the pair of 90-degree pulses here at this point. So when we do that, so you apply the 90-degree pulses to both this Hz and Xy, you get Hx and Xz. Okay, so you apply 90-degree pulse, so the Z goes to X and Y goes to Z. So therefore you get 2Hx Xz. So what does it mean? The Ft1 remains Ft1. Okay, what does it mean here? We have now transferred the magnetization back to proton from the X nucleus. Here magnetization was on the X nucleus. Now it has come on proton. So this is magnetization transferred back. That's why this antiphase term is required. If you have this antiphase term, when you apply a pair of 90-degree pulses to both the nuclei, then you cause this reverse the coherence transfer from the X nucleus, it gets transferred to the proton again. So you get 2Hx Xz Ft1. And ρ5, what happens in ρ5? So that is during this period from here to here, this antiphase magnetization which is on proton will get refocused again, because this is evolves under the coupling now, because we apply simultaneous 180 degrees of pulses on both the channels, on both proton channel and the X channel. Therefore, it evolves under the coupling. When it evolves under the coupling, it will get refocused. It will get refocused to form Hy. Okay, so we have to remember here the product operator formula, the way we have written earlier several times, right? 2Hx Xz goes to 2Hx Xz cosine pi j T1 pi j tau plus Hy sine phi j tau. This is what it will become. Now, if your tau is equal to 1 by 2j, then of course this will go to 0 and this will be 1. Here tau, I have written tau because, but there is a, in fact, there is a 2 tau there. I have taken for the whole period. For the whole period, see from here to here, that is 2 tau. If you put 2 tau, tau is equal to 1 by 4j, 2 tau is 1 by 2j. Therefore, when you put that in, so therefore this term will go to 0, first term will go to 0, the second will be simply hy. That is what I have simply written here, hy. And the ft1 of course remains. ft1 is what came from the evolution during the t1 period. Okay, therefore rho 5 is hy ft1. This presents in-phase proton magnetization. X can now be decoupled during the detection period because we have now got the in-phase magnetization. Therefore, there is possibility of cancellation of the intensities due to antiphase components. Therefore, we can decouple it. Thus, there will be no fine structure in the cross peaks. During the T1 period, there is decoupling due to the 180 pulse in the middle of the proton channel. And during the T2 period, we have to have broadband decoupling and we have there. Okay, therefore now you see we have excitation of the proton, detection of the proton. Therefore, the signal to noise enhancement will be gamma h by gamma x to the power 5 by 2 compared to what we had if we had X detection. Remember earlier when you had X detection, it was gamma h into gamma x to the power 3 by 2. Therefore, you have a total gain of here is the issue will be gamma h by gamma x to the power 5 by 2. That will be the gain with regard to X detection. No 1D X detection. 1D X detection means excite X, also detect X. So compared to that, you have here gamma h by gamma x to the power 5 by 2. So therefore, a substantial enhancement in the signal to noise ratio by this inverse kind of experiments. Okay, so now protons which are attached to C12 will be put along the z-axis. How does that happen? So if we're doing a natural abundance of C13, for example, there will be 99% of the protons will not be attached to the carbon 13. They will be on carbon 12 and they will not get transferred here. They will continue to flow like this. C12, okay, C12 attached protons, they will continue to flow like this, and at this point they will be put along the z-axis. They will come along the z-axis. Okay, and therefore during this period it will not make any effect with regard to the detection. It will not show up in the detections of the proton signal. Therefore, that is how you detect only the ones which are attached to the C13. Okay, all right. So now the protons attached to carbon 12 will be put along the z-axis, and that is before the last 2 tau period, and then it will not come back to the transverse plane, and therefore we will not detect it. Okay, here is an example of an experiment. So here this is on a protein. So but this is not carbon 13, this is nitrogen 15. This is on a protein which is called FKBP. Don't worry about what it stands for. These are all technical biological names. So along the so this says F3, F2, and this is actually F2, F1 it can be, but from a 3-dimensional plane, you take a projection, you get this F3, F2. So, but effectively it is a 2-dimensional experiment. So you have protons along the direct dimension and N15 along the F1 dimension. You have this cross peaks here. This essentially you will only see cross peaks. In HSQC spectra, you will not have any fine structure in the cross peaks, and you will only have cross peaks and one cross peak per residue. So if you have the protein chain, there are N15, all amide protons, they are all attached to 1,1 nitrogen. So therefore, there is no other coupling there. So therefore, one peak will be there for each amide group in your protein sequence. So you will have that many peaks here as there are residues in your protein chain. So this is the proton nitrogen 15 HSQC spectrum. And the right hand side is the proton carbon 13 HSQC spectrum. Okay, so here you see this is all this is aliphatic area. The aromatic area is not shown. Of course, the carbonyl will not be shown. Carbonyl will not show up here. So it's only the aliphatic area of the carbon here, and of course the aliphatic portion of the protons. These are only seen here. You have the methyls here, then the methylines here, alpha, then the alpha protons here, C alphas and things like that. So these are the details with regard to the analysis of the protein spectrum. These are just examples. Okay, so now let's continue with this. We do another experiment which is called among the heteronuclear correlation experiments. This is called HMQC. Earlier we talked about HSQC, right? Heteronuclear single quantum correlation spectroscopy. Now here we are talking about heteronuclear multiple quantum coherence spectroscopy. So it is slightly different. Ultimately, the result will be similar, but it is slightly different with respect to the pulse sequence. Okay. The pulse, it has a smaller number of pulses as you can see here compared to the HSQC. And how does this work? We start with the proton channel. So we start with the proton magnetization. Therefore, initially we have the HZ. Do I have the product operator description there? Yes. The description is there, but I will explain on the pulse sequence first. So you have the proton magnetization here, which is along the Z axis. You transfer it to the transverse plane by this 90-degree pulse. And during this period 1/2J, it will generate antiphase magnetization of proton X nucleus. Then we apply a 90-degree pulse only to the X channel. Now you don't apply it to the proton. When you apply it to only to X nucleus, then you get what is called 2HXSY. 2HXSY is not single quantum coherence. Okay, so you remember earlier what we had in the HSQC? You had HX, HZXY. HZXY it was, right? Because we had applied a pulse on both proton and X. And here we have not applied on proton. Therefore, that will remain as H because it started here as HY. It was HY here. And then when it comes here, it will be antiphase with respect to X nucleus. When we don't apply the pulse on the proton channel, it gets converted into HXSY. We will show that calculations soon. Okay. Now, during the next T1 period, what happens? This multiple quantum. Now, this is the multiple quantum coherence. Remember this. Earlier, we had described this. This product operator represents the sum of double quantum and zero quantum coherences. Okay, sum of double quantum, zero quantum coherences. And this will now evolve under the chemical shift. What chemical shift will it evolve? In principle, it should evolve as a double quantum coherence. Right? Double quantum coherence is the sum of the chemical shifts of the X and H. Okay, double quantum frequency. If you remember this energy diagram there, so this is the double quantum coherence, and this frequency is the sum of this plus the sum of this. So therefore, we will have the sum of the two frequencies, WH plus WX, omega H plus omega X. Okay, that will be the double quantum frequency. However, we are applying a 180-degree pulse in the proton channel in the middle of the T1 period. So from here to here, what happens? This 180-degree pulse refocuses the proton chemical shifts. Therefore, the proton chemical shift does not appear during the T1 period at all, because it is 180-degree pulse refocuses that proton chemical shifts. Therefore, from omega H plus omega S, from omega H plus omega X, which is the double quantum frequency, this will get removed. This will get removed. So therefore, we will only have omega X. So therefore, during this period, we will have only omega X. And at the end, the magnetization is still, the product operator is still double quantum coherence, okay, to HXSY. Okay, what about the coupling? Will it evolve under the coupling? Now, this is a thing which is a little bit more advanced, and you take my word here that the double quantum and the zero quantum coherences, or in general multiple quantum coherences, will not evolve under the particular coupling constant. If you are talking about H and X here, the JHX is not effective. It will not evolve under the JHX coupling. Therefore, we don't need to consider the coupling evolution at this point. But those of you who would like to derive this, you can actually derive this and show that the double quantum coherence, this kind of terms do not evolve under the influence of the coupling constant between the two. The calculation is a little bit involved, and but it can be done. If somebody is interested, I can show that calculation later. That is, you have to use matrix algebra a little bit to show that this actually does not evolve under the influence of the coupling constant. Okay, so but let's now take it as it is, that 2HXSY remains as 2HXSY here, except that it will acquire this FT1. What is FT1? FT1 is dependent on the chemical shift evolution. Because the T1 evolution does happen. Chemical shift evolution does happen. This chemical shift evolution will be to W omega X. So at this point, it is still double quantum operator and with the coefficient of FT1. When I apply this 90 pulse now only to the X channel, only to the X channel, I don't apply it to the proton channel. Therefore, the proton operator term does not change, but the X operator term will change to antiphase. When I do this, I get here 2HX XZ. So XY goes to XZ, HX remains as HX. Therefore, what I have done, magnetization flow has been like this, and now it will go like this. This is the flow of the magnetization. Okay, so it comes here. Now at this point, it is 2HX XZ. Now during the next period 1/2j, it evolves under the coupling because we have not applied any more pulses there. So it is all under the coupling of H and X. Therefore, this antiphase magnetization will now become HY. 2HX SZ will become HY. And after that, it is in phase magnetization. Therefore, you can, when you collect the data, you can decouple X nucleus without any problem. Okay, now this is explicitly written down here. Magnetization transfer pathway. You can appreciate these statements after I explained that what had happened there before. HZ goes to HY. The HY evolves under the coupling to produce 2HXXY, and then this remains 2HXXY, acquires this evolution coefficient FT1, which because of the evolution under the T1, and then this is then transferred to 2HXXZ after that last 90-degree pulse, and now this is proton magnetization, which is antiphase with respect to X. Now this will evolve under the coupling to give you HY FT1, and then you acquire with X decoupling. So you acquire a proton signal, decouple the X nucleus. Here it is, as I said here, HX multiple quantum coherence here. All this blue which is there is HX multiple. The 180 pulse in the middle of the T1 period refocuses the proton chemical shifts. Multiple quantum coherence does not evolve under the XS coupling. This is the statement which you have to take it on my words. If you want to derive it, you can derive it. It's a little bit involved. Therefore, I did not want to show that here. But in fact, I had actually included that as one of the questions, but the subsequently I said, okay, this is too demanding. So we dropped that. So, but those of you who are very keen on doing that, you can go ahead and try to show that this does happen. Multiple quantum coherence does not evolve under HS coupling. Therefore, there will be X chemical shifts during the T1 period. The proton chemical shifts are refocused. There will be X chemical shifts only during the T1 period. Multiple quantum coherence is converted to single quantum proton magnetization antiphase to X by the last 90-degree pulse. Then antiphase proton magnetization is refocused to produce in-phase proton magnetization, that is this HY. This is HY. Each of these things which are written here, I put them in words here. Every step here is written in words here, so that you can understand and follow what is going on there. This HY, this in-phase proton magnetization is detected with X decoupling. You can decouple this, that is here, you can acquire HY with X decoupling. Okay, so therefore you will get a spectrum which is similar to what you would get in the HSQC spectrum. Okay, now this is an experimental example here. So you have all regions are shown here in this area. These are the CH signals, these are the aromatic signals, carbon-13 CH3 signals there, proton carbon-13 correlation peaks. This is the complex spectrum. We will not go into this analysis. I'm just showing you of a protein this is. So these are but sufficiently well resolved. You can count here the number of peaks to see how many C alphas are there in this protein. This is the HMQC spectrum. Okay, now what are the differences between HMQC and HSQC? Okay, there will be proton-proton coupling evolution during the T1 period in HMQC. Okay, so in the, what is this here? Now we said during the T1 period, let's go back there. During the T1 period, that is from here to here, suppose you have a CH2 kind of a system. There will be proton-proton coupling. So the proton coupling that will evolve. Here the X coupling will not evolve, but the proton-proton coupling will evolve in the case of HMQC. Therefore, that will appear as a multiplex in HMQC. Proton-proton coupling will evolve into the spectrum. This results in splitting along the F1 axis, which hampers resolution. This does not happen in the case of HSQC. This is independently, each one is transferred to the X nucleus. The line widths in F1 dimension HMQC are dictated by relaxation rates of multiple quantum coherences in HMQC. In HSQC, they are dictated by single quantum X nucleus relaxation rates. Sometimes this can be of an advantage, but sometimes it may not be also. The peak shapes in HMQC are very complex because of multiple contributions arising from proton-proton coupling evolutions. HSQC peak shapes are pure absorptive. Therefore, this is another disadvantage of HMQC. Here you can lead to mixed phases here because of proton-proton coupling evolution, which is not explicitly calculated. You've shown only the transfer from proton to carbon-13 and carbon-13 back to proton and so. But during this period, proton-proton coupling evolution also will happen, and that will actually complicate the spectrum. Okay, so here's an experimental example. Here you can see already how the differences are. This is of the same system, menthol here at 7.05 Tesla. So this is the HMQC spectrum, this is the HSQC spectrum. So you can see this spectrum is not as clean as this one is. So this is because of the proton-proton coupling complications. There will be mixed phases here, and that can result to distortion of the peak shapes. Okay, so often therefore we record HSQC spectra as a standard. So, but sometimes you can record HMQC also. If there are mostly no such proton-proton complication, then of course both the things are the same. Okay, now there is one more heteronuclear multiple bond correlation. So far we are talking about one bond coupling. So this HC, CH or CH2 or CH3 or something like that, what we are talking about. This is one bond coupling correlations. But suppose you want to look at proton carbon-13, which is two bond or more. So this is multiple bond correlation spectrum. This is called as HMBC. So here what you do is the tau period can become very, very long, because you see the one bond coupling is like 100 to 150 hertz, depending upon what nucleus you are talking about. If you are talking about proton to nitrogen 15, it is about 100 hertz. Proton carbon 13, it can be 140 to 160 hertz. But multiple bond correlation, there is a two bond proton carbon 13 coupling can be very small. That can be about 10 hertz or even less. So in which case, if you want to give this 1 by 2j, you will have to give this delay 1 by tau is equal to 1 by 2j, right? That is what you have to give. So if you want to give that, then of course it has to become a very long time delay. And this is the calculation which shows here how much time you have to give for these individual things. So you'll have to give a long time delay to be able to pick up only those bond correlations. One bond coupling correlations can be suppressed. So here it is the peak intensity versus the tau that is given here. So for large tau, for large couplings, you need to have a small tau. For small couplings, you will have to give a large tau. Then of course you will pick up with those ones. So, okay. Now these are the simple experiments for direct correlations of single bond and multiple bond correlation experiment. There are certain other improvements in the HMBC pulse sequences. I have not gone into that. I have only given you the basic experiments which are there. Improvisations are always possible. You can design experiments whereby you can suppress some of those things and retain only the ones which you need to do. Okay. Now, you can do something more than that. After that, what you can do is you can combine two kinds of experiments. Like for example, here I am combining HSQC and TOCSY. So heteronuclear single quantum coherence, I am combining with the TOCSY. TOCSY is proton-proton transfer. This is heteronuclear transfer. So what you do is you transfer from proton to the heteronucleus. Okay, then you complete the heteronucleus experiment. Then before you actually detect it, you put a TOCSY sequence there. See, until here it is HSQC. Until here it is HSQC. In the HSQC, you were able to record the FID directly from here and decouple there. But instead of doing that, what we do is we introduce a TOCSY pulse sequence there. So TOCSY pulse sequence, what it does, suppose you come up to the particular proton, and if there is a proton-proton coupling, it causes the relay through the proton-proton network. It causes the relay through the proton-proton network. And therefore, you have additional information from one particular carbon. Suppose I have a carbon like this. So from you come up to a particular proton, and now if this proton, say another one, this is like this. So you went here and come back there. Now you have another coupling here, for example, then it can relay through this. So from this proton, it can relate to this through the proton-proton coupling that happens through the TOCSY. So therefore, you will see correlation for this carbon. You will see correlation not only to this proton, but also to this proton. So you will see both the things, and that is why it has the toxicity there. So you have the correlation peak here. So you have the carbon 13 at one particular point. You will have this particular peak on this proton here, and you will have another peak here, which is related to this proton. Okay. So therefore, this is a toxic relay. This is the toxic relay, and here you have only the direct peak. The direct peak versus the toxic relay can happen in this, and that has an advantage because you can see the network of coupled protons in a particular experiment. So that is the purpose of doing this kind of a mixed relays, mixed coherence transfers. You on the one hand, you do a coherence transfer through the heteronuclear correlation. You start from a particular proton here and end up to that particular proton through the X nucleus. You come back to the same X proton, remember, you come back to the same nucleus. You go here and come back there. That is what is this HSQC is doing when you detect it. But in this case, before you detect it, you do a relay using the toxi. So therefore, you will have a relay going from here to here. So you see correlations of this type. So this is the benefit of this. You can actually do networks, identify the network of coupled spins in a particular molecule. Okay, here is an illustration there of the experimental spectrum. In fact, these examples can be discussed in more detail in practical classes. So that is, someone can go through it in greater detail. So here is the HSQC spectrum of this particular molecule. So you see so many peaks are there. This is the one-dimensional proton spectrum on the top, and on this axis you have the fully decoupled carbon-13 spectrum. Okay, this is a carbon-13 spectrum, fully decoupled. It's all singlets. Various carbons are there. You have so many carbons there. You have all those carbons are represented here. Now, from the carbon, you are seeing two correlations. These are direct peaks. These are direct. That means at this point there are two carbons, which is a proton here and a proton there. Okay, so there is an overlap of two carbons there. So you come to this one, there is only one. So here, for example, you see 14. 14 is this carbon. This carbon is appearing here. That is this here. And 15A, 15B, those are here. This is 15, and these, okay, there are not two carbons. They are actually connected to two protons. The single carbon which is connected to two protons, HA and HB, and therefore those two protons are here. Okay. But if it can happen that if there is an overlap of two carbons, that also can show up in the same manner. In this case, the 15 is attached to two protons and they are non-equivalent. Therefore, you see 15A to 15B. Now, let us look at 11. See, 11 is here. Where is 11? 11 is also attached to two protons there. And therefore, these two peaks which are coming here, they are connected to carbon 11 and carbon 11 to 11A and 11B. And then at the same place, nearly the same place, you also have this carbon 17. The 17 is here. The 17 also has two peaks. Probably the two are equivalent there. These two protons are equivalent there. Therefore, they are having the same place. They are not showing two different peaks. So depending upon what the chemical shift equivalences are, therefore you will see different ones. For example, see 13 you see. Where is 13? 13 is here. 13 is attached to only one proton, and that is showing you one peak. This carbon 13 is here, carbon is here, and the proton is here. And that is, so like that, you see, you have this in the HSQC spectrum, all the carbons are very well resolved, and you have the corresponding proton peaks at the respective positions. So 1, 2, 3, 4, all these carbons are very well resolved, and they are identified on the basis of their coupling networks. Now, on the right hand side is the mixture of this HSQC with the toxin. You do the next step. The next step is, so what we had here, this particular one was 15, right? The topmost one was 15 carbon. The 15 carbon had two protons that generated two correlations here to HA and HB. But these protons, HA and H15 are connected to the proton of 14, right? There is a 3-bond coupling to the proton. Therefore, there is a relay from 15 to 14 proton. And that is what you can see here. It should go, there is a 14 here. So from the 15, these are 15A, 15B, carbon 15 is here, 15A, 15B, and the relay through the proton coupling network to 14 here, and also to 16. Where is 16? The 16 is here. Oops. 16 is here. So therefore, it's a relay. The toxin, there is a relay of magnetization, right, through the proton coupling network. So you also see to the 16 there. So similarly, one can analyze the various things. You can look at this one here, which is this one, 20A. This one is 20A probably. So 20 and this is 12 here. And where is 12? 12 is here. Okay. Now 12 is, this carbon is, okay, now let's look at the 12 is here. Okay, this is 12. And 12 is showing relay to this one, and this one. And which is this one here? This is 16. 12 is connected close to 16. Where is 16? 16 is here. No, it may not be 16 then. There must be some other one which is there, or this is a weak one there. And it is showing it to 14, it is showing. 12 is showing to 14. 12 is showing to 14, that is here, to showing to this. This is proton-proton coupling there. Proton-proton coupling there. And it is also showing to 11. So this is 11 here. 12 to 11, it is showing to those ones there. Yeah. So therefore, you can see by looking at these relationships, you can identify the various kinds of coupling networks in your spectrum. Okay. So now let us go to the HMQC TOCSY. You can do the same thing in HMQC TOCSY also. That was HSQC TOCSY. The pulse sequence remains the same, except they were added here the TOCSY part. The TOCSY part added here, it gives rise to a different experimental spectrum. Okay, so now we can combine that. We combined earlier with the TOCSY. Now we can combine that with the NOESY. So you see, until this period, it was the HSQC. Until here, it was HSQC, right? Now from here to here, it is the NOESY. You have the mixing time here, the tau m, mixing time. So you put the magnetization along the z-axis at this point, and then you have the mixing, and you, after this, NOE transfer happens, then you collect the signal. In the previous case, we had the transfer from here to here using TOCSY pulse scheme. Now here we use transfer from the H proton to another proton through the NOE. So therefore, this also is possible. You can identify these in your NOESY spectrum. So this has the structural information. The previous one has spin system connectivity information, and here you have the structural information, because this will tell you which protons are coming close by in space, and the rest of the thing remains the same. So here is an example here of this particular molecule. This is HSQC NOESY. The HSQC NOESY, what is the, this is a small molecule. Notice here, the red peaks, the black peaks which are present here are the standard HSQC peaks of this molecule. All the black ones here, these are the HSQC. You have the carbons here on this axis, and you have the all these individual things which are the black peaks are the HSQC peaks. Now let us look at this here. You have 15A and 15B. So this is, there are two protons attached to the carbon 15. It is carbon 15. Carbon 15 is here. It has two protons, HA and HB, and those ones are showing you this peak. Those are the HSQC peaks. And then what you are seeing many red peaks. Red peaks are negative. These are NOE peaks. The relay is happening through NOE. Proton-proton NOE. Okay. Proton-proton NOE in small molecule will appear in this as negative peaks. The HSQC peaks are appearing as positive peaks. The NOE peaks will appear as negative. This is an extremely useful feature, because you can figure out which are the NOE peaks and which are the HSQC peaks. So you can see so many peaks here which are negative, which are connected to 15. The 15 is connected to 14 through NOE. See, 15 is connected to 14 through NOE. That is this HBHA to this proton. Okay. And it is also connected to 20. And what is 20? Here. See, from here to here. It is connected to these two protons. These protons are close by in space to these two protons, and therefore you are seeing to 20 here. It is showing only to one of the 20s. Okay, 28 is not showing. So this probably is further. So it is showing to only one of those. Okay. Now similarly, you can see it is also showing to 13 here. Where is 13? 15 to 13. This one. This one is close to these two protons. Okay. So therefore, you are seeing a peak to 13. So therefore, you have the structural information here. From the HSQC, you have identified the peaks which are close by in space. These are extremely useful things to see whether you have got a molecule which is designed to synthesize, whether you got that molecule or not. or you can identify the peaks on the basis of such kind of correlations if you knew the structure. So if you did not know the structure, you can determine the structure on the basis of this kind of correlations. So therefore, you see so many NOV peaks are seen here from the HSQC NOESY spectrum. So therefore, this is a very useful feature in structure determination. So HMQC NOESY also in the same manner. So up till here it is HMQC, and then you have added here the mixing time. This is the tau m. This is the mixing time of the NOESY part. From here to here it is the HMQC part. Here it is the NOESY part, and we collect the data here as a function of time. Okay, so this finishes this one for lecture 14. Now we go to the 15. Hello, where did we go? This will actually carry forward to the previous one.
Just ask the participants if they
have any questions,
they can ask question, or at this stage you can take break,
Yeah.
break and then start. Any question you write? No, sir.
Did they answer? No questions?
No response, no? You write from our side, any question you write.
Yeah, 15. Should we start and then take a break, or what? How you want?
As you feel, which one will be comfortable?
We can start. We can take a break after 5-10 minutes.
That's okay. Time is there. Yeah.
So we are going to three-dimensional NMR now. After this, maybe we take a break here, because we are going to start up a new topic here.
Yeah.
New topic here.
We just tell them.
Yeah, yeah.
Just 5 minutes break.
5 minutes break, and then we start the next one.
Because new thing is coming up, so
Run now. Okay, so let us continue. Now we are going to enter into a further step, a new extension beyond natural extension from the two-dimensional NMR, and that is the three-dimensional NMR. Okay, as described previously in a generalized case, so three-dimensional NMR means there will be three frequency axes, therefore there will be three time axes. So, and how do you generate the three time axes? And that is indicated here. So you have the usual preparation period there, which is there in every experimental sequence. And we have a T1 evolution period, one time variable, independent time variable. Then you have the mixing here, first mixing period. Then you have the second time variable, which is independently incremented. This generates the second time variable. Then you have the second mixing period here, M2. And then finally you have the detection T3. So FID is collected only during the T3 period. So you get a series of FIDs and for systematically incremented T1 and T2 values. Okay, so you may decide to do a large number of experiments along T1, a large number of experiments along T2, and then of course you detect the T3. Therefore, obviously, you will now have a cube or cuboid of the FIDs. So you have several FIDs and as a function of T1 and T2. Evolutions during T1 and T2 contribute to a detected signal. And the mixing periods transfer information between the two connected time periods. So M1 transfers information from T1 to T2. M2 transfers information from T2 to T3. So therefore, whatever is transferred from T1 to T2 can get carried forward into the T3. Therefore, you will have a three-dimensional correlation map. So the correlation map in the three-dimensional spectrum. Of course, you cannot physically represent it by drawing a picture in the because there are only three dimensions there. Intensities are represented they are in the fourth dimension. So there are three frequency axes and intensities are in the fourth dimension. That is, you cannot represent it on board that way. So is the number. So you have a three-dimensional data body, three independent time variables. Therefore, you require a three-dimensional Fourier transformation to generate a three-dimensional frequency spectrum. Okay. So let's see typically how it looks. This is a homonuclear 3D NMR experiment. You have three frequency axes there, and for a typical spin system of ABC, so there will be all kinds of transfers: A to B, B to C, A to C, C to B, etc., etc., etc. So you'll see how many peaks you will have. So 3 to the power 3, because three dimensions, and each of them in each dimension you can have a correlation from each one to the other. So you will have all the three couplings which are present. You will generate a spectrum which is like this. So, okay, so it will have 27 peaks, 3 to the power 3. It's quite a complicated spectrum it will be. Now, depending upon what kind of a spin system you will have different kinds of patterns. Okay, these are just schematics. If you have the ABC linear three spin system, then M1 and the mixing periods M1 is not equal to M2, then you will have this. But if the mixing sequence M1 is equal to M2, this is the same sort of a mixing, then you will have a spectrum which is like this. So this becomes quite a complicated homonuclear 3D NMR spectrum. However, I just put it here for your information. And today, of course, most people don't do homonuclear 3D experiments. You go to heteronuclear experiments. These are relatively simpler to analyze. But I given you certain examples how the whole thing evolved. So when I say here COSY, the first transfer is also through the COSY transfer, second transfer is also COSY transfer. See, in heteronuclear HSQC TOXY, what we saw, HSQC TOXY, the first transfer was a HSQC transfer, the second transfer was a TOXY transfer. But there was no independent time increment. The process of two mixing periods were there, but there was no independent time variable there. So here you have an independent time variable also that generates a three-dimensional spectrum. So you have one time variable here, another time variable here. This is the first COSY part, the second COSY part. See, the mixing here is simply by the 90-degree pulse. Therefore, this is called as a COSY. Now you can do a selective COSY. That means you apply a selective pulse here and selective pulses here and here. That means you pick up a particular portion of the three-dimensional spectrum, because you are applying the pulse only to a small segment of the protons, and you apply these pulses also to the some segment, and finally you collect it here with a hard pulse. This is similar to this, but this will be selective COSY. You can also combine a NOSY and COSY that way. The first portion from here to here is nosy. Okay, is the selective part here, selective pulse, non-selective pulse in the mixing time, and a selective pulse here. And this is the nosy part, and then here it is the cozy part. So you will have the cozy part, and this is the T3. Data collected here is T3. So for each one of these, we have an independent time variable, T1, T2, and then you have the T3. So this generates a nosy cozy. Similarly, you can also have a nosy toxy spectrum. So this is the nosy part. From here to here, it is the nosy part. And then from here to here, it is the toxy part. Okay. So, and the T2 is introduced here because you need to generate an independent time variable. After that, the toxy will come. So you can do nosy toxy. Okay, this is nosy toxy. This is also nosy toxy, except that now you apply the selective pulses here, here, and there to pick out a small segment of the entire spot. Now, the hetero-cozy, this is the hetero experiments. Okay, we will not go into the discussion of the details of all of this. I'm just listed here for your information, and you can look at these things at leisurely, some of it. The hetero-cozy, hetero-cozy, toxy, heteronuclear experiment. These are the exchange experiments here, homonuclear exchange experiment. Okay, so you have a whole lot of these. I've listed only a small number. You can make all combinations of the mixing sequences, evolution period, the preparation periods, and generate a whole number. There are nearly tens of pulse sequences can be generated. So this is only indicative of how one can generate different kinds of combinations of the pulse sequences. Okay, but why does these homonuclear experiments are not that popular? The reason why I'm showing you here is by this slide. So consider a particular 3D experiment. You have, let us say, 256 T1 increments and 512 T2 increments, because these are independent variables, right? Independent time variables. Okay, and your acquisition time is, let's say you're collecting 1024 points, and the T3 is, corresponding to that, you have the T3 period. 1024 time points will correspond to 0.2 seconds of your acquisition time, let's say. And you have a relaxation delay of 1 second. What is relaxation delay? Relaxation delay is the time you give before here, before you start, before the preparation, during that period. That is a relaxation delay. That is common to every experiment. Whichever experiment, whether you do 2D, 3D, 4D, 5D, whatever you do, that relaxation delay is common to every experiment. So here you have, because you have to allow the system to relax back to its original equilibrium state, and then you start the experiment. Okay, so if you did that, let us say you have 1 second relaxation delay, and this will depend upon what? This will depend upon the T1 values. The T1 values or the T2 values, you have to optimize on that. So if you are working with the small molecules or something of which has a relaxation time of about 0.2, 0.3 seconds or so, you have to give a 1 second relaxation delay for the system to come back to equilibrium completely. Now let us say you do minimum scans of 4, because you need to do this for phase cycling, for eliminating all the phase errors, artifacts in your pulses and artifacts in your receivers, things like that, inaccuracies, not artifacts, inaccuracies in this. Then you'll have to collect a minimum of 4 scans. Now you see how much time it will take. You have total of 6 scans. These are 2 dummy scans. These are to achieve a steady state. 4 plus 2, 6 scans. And what is the time for each scan? 1.2 seconds. This plus this, 1.2 seconds. Then you have 256 times this, 512 times this. So many seconds. That is 11 days. For one experiment, it takes 11 days. And who has that sort of a time? For one experiment, if you do, you don't know whether it will work or not finally, whether you will get the desired resolution, desired experimental information, or you don't have this kind of a time. It is also very demanding on the spectrometer time, and therefore these are impractical. And that is why the heteronuclear experiments have become very popular. So heteronuclear experiments, you have one axis, you have the X nucleus, and along the other 2 axes, you may have the proton, or you can also have another nucleus over there. So typically, if this is a 2D experiment here, proton, nitrogen 15 on this axis here, this is a typical HSQC spectrum, what you might have, F2 and nitrogen here. And in the 3D experiment, you have on the 3rd dimension, also have the proton. Typically, when you're detecting a proton, it comes along the F3 axis. The F3 axis is the detection sequence. Okay, you always want to detect on proton because you get the maximum sensitivity there. We are seeing that in HSQC or HMQC or whatever indirect sequences, you collect the data on proton. Whatever you collect there, that is a T3 data point. The T3 will show up as F3. In the two-dimensional case, you have only two frequency axes, F1 and F2. The F2 is proton, F1 is nitrogen 15. In the three-dimensional experiment, you have the F3 as proton, F1 is nitrogen 15, and F2 can be proton. So if you have these two, then what is going to happen here is, then you establish correlation from each of these protons, each of these peaks here, into another set of peaks which are along the F2 axis. F1, these same four peaks are present here and here. These peaks are the same. These are the same. So now what you have done here is, you extended this information along this another proton axis. This extension can be due to what? It can be due to the toxi. So from this particular proton, you may have a toxi relay to other protons along this axis here. This is a proton axis. Therefore, from this proton, from this particular nitrogen, from this proton, you can have a relay to other protons, which is according to the toxic coupling or the NOE coupling or whatever it may be. So these ones can be different intensities depending upon the kind of interaction that you are looking for. So therefore, this will improve the resolution in the spectrum, also increase the information content in your spectrum. Therefore, this kind of experiment are quite popular, and these have been very, very successful. Okay, now how do we do this combination? So we have seen here the 2D toxi experimental sequence. This is a normal 2D toxi experimental sequence, and this is the normal 2D HSQC sequence. And we have seen how to combine this in the 2D toxi HSQC. What we did, we simply added here the toxi-pulse sequence here further in the 2D HSQC. We did not put the T2 time, another time variable there. So now we have to put a time variable. We make a combination, the 3D toxi HSQC. We want to combine these two pulse sequences. So from here to here, it is the same as this toxi. Yeah, from here up till here, that is this here, right? Now, instead of collecting the FID here, what we are doing now is, we do a HSQC sequence. From here to here, it is a HSQC sequence. Okay, but in between, we have, during the HSQC, we have this T2. Here in the toxi, we have the T1 here. Okay, mixing sequence. So this is the end of the toxi. And from here to here, we have the HSQC. We have another time variable here, which is T2. And we collect the data here as T3. Therefore, this is how we generate three time variables in a combination of 3D toxi HSQC. The first part is the toxi pulse sequence. You have the time variable T1. Remember, I am just repeating this. 2D toxi is here. You have the T1 period here, and the data collection happens here. Now, so therefore, the toxi actually ends here. Toxi actually, transfer of information happens here. This is the data collection. In the data collection, we actually have to do it at the end only. So up till here, we have the toxi part. So that is this here. Now from here to here onwards, this is the inept sequence of the initial HSQC inept. Then you have the T2 here. There's this middle 180 degree pulse in the middle. Then it is the refocusing period here, from here to here. And then you have the decoupling. So this is the 2D HSQC. So instead of this pulse here, we have the magnetization already obtained in the transverse plane. The purpose of this pulse was to create transverse magnetization, but that is already here. So we don't need this pulse. We don't need this pulse when you make a combination here. So we extend it delta, this 180 delta, and this portion is the same. The T1 is now T1 becomes T2 here, because T1 we have already used at this point, and the T2 is here, and this portion is this two pulses here, then these two pulses are these two pulses there, and then you do the decoupling and collect the data finally at T3. So therefore, we have the information of toxi mixing through the T1 and the HSQC mixing through the T2. Therefore, you generate a three-dimensional toxi HSQC spectrum. And similarly, you have the 3D NOESY HSQC. So NOESY HSQC. Now, what is NOESY HSQC? So from here to here, until here, it is a NOESY part. Until here, it is a NOESY part. Right? The mixing has happened, and this is to observe it. Therefore, now from here onwards, from here to here, it is the HSQC. So you have the first, you have the NOESY part. From here to here, it is the NOESY part. This last 90 degree pulse is a part of the inept sequence here. Part of the inept sequence of the HSQC. This is the first inept. Then you have the T2 period here. Okay, this is from here to here, it is T2. Then you have the refocusing here. Then you have this, at this point, you have the refocused proton signals. And then after that, you decouple here and collect the data as a function of T3. Okay. So this is how you generate a three-dimensional pulse sequence. You have generated three independent time variables. In the nosy, you have the T1 time variable, and the HSQC part has the T2 time variable, and the detection here is the T3 time variable. So therefore, different kinds of mixings can be achieved here in the three-dimensional experiment. Okay, so we can do it in the two-dimension also. In the two-dimension meaning what? In this case, you don't make a systematic increment here, then it becomes a two-dimensional increment. You have only one time point, then it is a two-dimensional experiment. That is like taking a projection. If you have only one time point, it is like a projection along that particular time axis. So you generate a 2D spectrum. So therefore, this is a 3D can be converted into a 2D by taking a projection along one of the axes, which means you are not taking any increment over there. And this is the decoupling along C13 or nitrogen 15. So here you see the example, experimental example here of a nosy HSQC. The nosy HSQC is, this is a typical HSQC spectrum, two-dimensional HSQC spectrum. And if you take this plane here, this is basically the projection of those things, and the same as this. This bottom here, which is the same as this, all these peaks which are there are the same as this. Now for each one of those, you have pulled them along this third dimension. This is the additional dimension, proton dimension, as per the NOEs. From this particular proton, your peak, you are seeing NOEs to various protons here. Okay, so this peak is appearing somewhere here, and you have another peak which is down here. Then you have the peaks here, peaks here, peaks here. So you see the proton is showing NOE correlations to so many of these other protons there. And these are resolved on the N15 axis here along on the basis of the proton N15 correlation there. So therefore you see the information is now spread out in a cuboid. Okay, it is not, so you have two types of information there. So you have two types of information. One is the HSQC correlation, which is allowing you to separate the peaks on the basis of the heteronuclear correlations, and then using the nosy to relay the information through the proton coupling network. So remember, these are proton-proton NOEs. These are not heteronuclear NOEs. These are proton-proton NOEs. The J coupling correlation appears in the form of HSQC, and the NOEs are proton-proton NOEs. Therefore, this is structural information. Then the TOXI HSQC had the spin system identification, and the nosy HSQC will have the structural information in the molecule. So here is an illustration there. So this is the plane from a three-dimensional spectrum. Okay, so this is a two-dimensional spectrum. You have here proton along this axis. This is the nitrogen 15 along this axis. This is a typical HSQC spectrum. What you do is you take a particular plane through at some particular plane in the three-dimensional box. In a three-dimensional box, you take a particular plane. So in that particular nitrogen plane, you have so many protons. Suppose I take a plane here. If I take a plane here, so you have so many protons there, here. So many protons are there, right? All those protons are appearing on this diagonal here. Okay, they are all protons appearing here. And what are these there? These are the correlations. These are the NOE correlations. NOE correlations between these various protons in the two-dimensional. See now you see here, this is also proton, this is also proton. We have taken a particular plane through this in the from the three-dimensional box. The three-dimensional box was here. So along this axis we have the nitrogen here. So here I have the proton. Here I have the proton. Here I have the nitrogen 15. So I take a particular plane. Let's say a particular plane through this here. Okay, and that is what is shown here. So that particular plane, you have so many nitrogen. Now you look at those particular protons and the proton-proton correlations. Take it as a two-dimensional nosy spectrum, considering those many protons, which are present at this particular N15 chemical shift. So if you are looking at the two-dimensional spectrum of that, then you have so many protons, those protons which are present here. The two-dimensional nosy spectrum will look like this, right? So each of these protons which are present here, they are showing correlations to so many other protons in your molecule. And these are the NOE correlations. Okay, so therefore you can quantify this. Therefore, you will have several planes like that. Depending upon which plane you take, you will have these different kinds of peaks. In a normal 2D nosy spectrum alone, all of them will be coming together. So you will not be able to resolve them. So now you see, they all have got separated out. So depending upon which plane you take here, which plane you take, a plane here, plane here, plane here, plane there. You can see, I mean, they can see my hand here, right? If I put like this, they can see my hand.
No, sir, we have to.
Oh, I have to show. See, if I take a plane here, oh,
Otherwise, you can. Different arrows.
huh? What?
What's coming? Okay. Put it there.
Hmm?
I guess it's
It's coming? No?
coming.
Where it is?
So. Yeah, slowly.
Yes. So you can take cross sections at various nitrogen 15 positions. You can take a plane here, plane there, plane here, plane there. All of these planes are the ones which are seen here. Each one of those planes will produce two peaks like this. So in a normal 2D spectrum, all these planes will be superimposed. So it will result in a very complex spectrum. Okay. So therefore, that is not analyzable. Now in this case, they all get separated out into different planes from the 3D spectrum. Okay, so you can put them, you can analyze individual planes here, and that will improve the resolution and accuracy of your analysis. Okay, so this is the advantage of doing experiment in three-dimensional mode, three-dimensional HSQC, nosy HSQC spectrum. Okay, so those were where we had one heteronucleus and two proton axes, right? In those experiments, what we saw, Toxi HSQC, nosy HSQC, we had one heteronucleus and two proton axes. Now we can go further to triple resonance experiments. Triple resonance experiments are much more demanding in the sense that on the spectrometer wise, hardware wise, also you need more infrastructure. In other words, so as the word triple resonance says, there are three channels. One channel is for proton, which is where you actually measure, and one channel is for one nucleus, another channel is for another nucleus. And typically these are for carbon 13 and nitrogen 15. So all these experiments were designed primarily for protein spectral analysis. So these are a large number of experiments. There are hundreds of pulse sequences here. So I am only showing you a few of those experiments which have been extremely useful, and people continue to design new pulse sequences depending upon the needs. Now, so let us look at some of these pulse sequences, what these ones are. So this, as I said, this will require three channels. All these experiments, that's why they are called triple channels. You have channel here, this is a proton channel, and you have a nitrogen channel, and you have a carbon 13 channel. So spectrometer should have three channels, okay, so that you can independently apply pulses on the individual channels. Data is collected always on the proton channel, okay, and you apply various pulses in the proton channel, in the nitrogen, of course on the proton channels, in the carbon channel, depending upon the way you want to transfer magnetization. The inept transfers are used. All the time inept transfers are used from one nucleus to another nucleus. Want to transfer from proton to nitrogen, you use proton nitrogen inept sequence. Proton to carbon 13, proton carbon 13 inept sequence you use. So therefore the inept becomes an integral part of all of these pulse sequences. Okay, so therefore in these various steps, what one talks about is what is the magnetization transfer pathway? How is the magnetization transferred from one nucleus to another nucleus, and how is the information derived? So in large proteins, of course, you will have very complex spectra. You have so many kinds of peaks, and to analyze all of those, you certainly require the 3D experiments, number one, and also triple resonance experiments, because you want to make use of dispersion of all the three nuclei: proton nuclei, carbon nuclei, and nitrogen nuclei. All the three you want to resolve. See, in the previous case, you made use of the dispersion in the nitrogen 15 to resolve your proton-proton peaks. the proton-proton correlations which are there in your 2D Nosy spectrum, proton-proton Nosy spectrum. To improve the resolution of those ones or the dispersion among those, you use the nitrogen 15 chemical shift. Nitrogen chemical shift was used to disperse the peaks in different planes of a 3D spectrum. Now we want to make use of additional nucleus, and that is the carbon-13. Carbon-13 nucleus also we would like to use in case there are further overlaps in the previous cases. Therefore, these are called as triple resonance experiments. So one of the most early ones which were described are listed here. This is one of them is called as HNCA. HNCA stands for, on one axis you have the proton, that is the amide proton. One axis you have the nitrogen 15, and the third axis you have the carbon, which is primarily C alphas. C alpha carbons are there in that particular axis. And how does this experiment work? So you have this proton channel experiment going on here. You have the polypeptide chain indicated here. So you always start from the proton. You start from the proton. Yeah, you start from this proton here. You transfer magnetization to this nitrogen. Okay, to this nitrogen. You can see this cursor here. From this proton, you transfer to this nitrogen. And this is through the inert sequence, as in the previous cases. And then what you do is you transfer the magnetization from nitrogen to this two C alphas. This is one C alpha here and another C alpha there. To these two C alphas. Okay. And then after that, you label this. So you can, first you transfer from proton to nitrogen, you label this frequency. This will be incremented. For example, it's a T1 increment, for example. This you do a T1 incrementation here to frequency label this. You transfer this to the C alphas, and then you label the C alphas. That means your T2 increment will be in the C alpha dimension. C alpha frequencies are labeled by T2 incrementation. T1 incrementation leads to nitrogen frequencies. And after you label this carbon-13, you transfer them back to the nitrogen here. Then again from here to the nitrogen. And from nitrogen, you come back to the proton and you detect the proton. So this proton will be the T3 dimension. The T3 dimension here. You start from the proton, transfer to the nitrogen. This is the T1 incrementation here in the nitrogen. Magnetization is when it is on the nitrogen, you make a T1 incrementation, and then from there you transfer to the carbon here to the C alpha, and then to this C alpha. Then this is then you do carbon incrementation. This is the T2 time period. So it is the carbon incrementation there, and after that you transfer it back to the nitrogen from here, and then also from here. Then from that nitrogen you transfer it back to the proton, and you collect the data as proton. See, so this is called as a out and return. Okay, it goes out and comes back. So that is the strategy here. So this actually results in triple resonance experiment. I will explain to you with the pulse sequence a little bit later, but I'm telling you the strategy, how the magnetization transfers can be manipulated by designing your pulse sequences. So from where to where you want to transfer the magnetization, that determines how your pulse sequence will look like. Okay. In every case, you can use inept pulse sequences. By and large, inept sequences used for every transfer. We take another example here, HNCOCA. Here, you start with the amide proton once more here, and transfer to the nitrogen. And this is the T1 incremented here. Therefore, this is the nitrogen will have a frequency, F1 frequency. Now, from nitrogen, you don't transfer to the C alpha directly, you transfer to the carbonyl. See, in this case, what happened was, you have the direct coupling from nitrogen to C alpha. This is a 2-bond coupling, and this is a 1-bond coupling here. Okay, using this 1-bond and 2-bond couplings, you transfer directly to the C alpha. Now, what you do is here from the nitrogen, you transfer to the carbonyl. How is it possible that you transfer to the carbon, only the carbonyl and not to the C alpha? This is because in the carbon frequencies, if you remember the carbon spectral region, carbon spectra, so you have this aliphatic here, the aromatic here, and the carbonyl here. This is the carbonyl here. This is aliphatic here, chemical shifts. Okay, and these are aromatic. So we don't worry about the aromatic here. We have the aliphatic proton to the nitrogen, nitrogen to, we can apply pulses either to the aromatic ones or to the aliphatic carbons or to the C-carbonyl, because this spectral width is very large. They are very far apart. Therefore, without any difficulty, we can apply pulses only to the carbonyl or only to the C alphas or only to the aliphatic ones. So we can do that. And that's how it is possible to select these transfer pathways. So here what we do is we apply pulse to the carbonyl. We don't apply from here. When you're making inept transfer, we transfer from nitrogen to carbonyl. We don't do an inept transfer from nitrogen to C alpha. We do an inept transfer from nitrogen to carbonyl. From the carbonyl, you transfer to the C alpha. Okay, so then it goes in one direction. From carbonyl, this is a one bond coupling here. You make use of the one bond coupling, you transfer to the C alpha, and then you do a T2 incrementation here. Nitrogen is a T1 incrementation, do a T2 incrementation here, and then you come back to the carbonyl, come back to the nitrogen, then come back to the proton and detect as T3. Okay, during the third frequency axis. So this is how you can design your pulse sequences there. And of course, we will not want to explain to you all of these. Each one of them can take 1 hour. So therefore, we will not go into those much of detail. But however, I will show you typically how the spectra will look like. So this is, you have one frequency axis, this is the proton axis here, then you have the nitrogen 15 axis here and the carbon axis there. So you have the peaks dispersed in a cuboid, and you can take projections on any of these planes. You can generate that kind of 2D correlation spectrum. Okay, so here again I have stated the same things which I explained to you earlier in a slightly more explicit manner. A few of those: nitrogen, amide proton to the nitrogen, nitrogen to the C alpha to the nitrogen, nitrogen back to the proton, and similar manner. HNCO is now is a shorter experiment here. Proton to the nitrogen, label the nitrogen here, nitrogen to carbonyl, you label the carbonyl here, then back to nitrogen, back to proton, and you detect it here. Okay. Similarly, all of these arrows indicate the nitrogen magnetization transfer pathways in different pulse sequences. Okay. Why these experiments are so successful? Because here all of these are based on magnetization transfer on the making use of one bond and two bond couplings only. These couplings do not vary too much. Therefore, it is possible to optimize these experimental sequences by choosing the appropriate delays as per the coupling constant. Remember, for the inept experiment, the effective transfer was 1 by 2j. You needed a tau delay which is equal to 2 tau delay 1 by 2j, or tau is equal to 1 by 2j if you are having tau 180 tau if you are saying, but total time is 1 by 2j. This is now the proton couplings vary a lot, from 3 hertz to 12 hertz, 13 hertz, whereas the one bond couplings do not vary so much. Therefore, you can, without any fail, you can cause a transfer pathway. You can effectively transfer magnetizations at every step. So there will be not too much of a variation there. So except the two bond coupling. The two bond coupling is somewhat more variable, goes from 4 to 9 hertz. This one bond coupling is okay. See, the one bond nitrogen proton coupling is 90 to 95 hertz. Okay. And nitrogen to C alpha two bond coupling is 4 to 9 hertz. Nitrogen to C alpha one bond coupling is 7 to 11 hertz. And nitrogen to carbonyl is 15 hertz. And carbonyl to C alpha is 55 hertz. And proton to and proton to carbon is 140 hertz, and this C alpha, C beta, this is the carbon-carbon coupling is 35 hertz. These ones don't vary much. Therefore, it is easy to optimize your pulse sequences making use of these numbers. Okay, let me explain this to you here in somewhat greater detail. Particular constant time HNCA experiment. So this is the pulse sequence is in full detail is given here. Earlier, I've only indicated to you the pathways, how schematically how the pathway happens. Okay. Now let us see here how it actually works. Constant time HNCA experiment we will see here. Now remember, from here to here it is the inept sequence. The inept sequence between what and what? Inept sequence between proton and nitrogen. So it starts with the proton magnetization here, and you make use of this inept sequence. Therefore, at this point, you will have the nitrogen magnetization. The proton is transferred to the nitrogen at this point. Now we label your T1 by 2. So you have a systematic time incrementation of frequency labeling in the T1 increment. But this is a constant time experiment, meaning I keep the time from here to here as the same. In the CT COSY, if you remember constant time COSY, you had this a constant time with delay from here to here. So from here to here is the constant time period, because you see your total of these ones, it is T. T is the constant time. So here you have a T1 by 2, and you apply simultaneously pulses on proton at this point, 180 pulse and a 180 pulse here on the carbonyl. I will explain to you what these ones are for. And then you have the period capital T by 2. Then you have the 90-degree 180 pulses on both nitrogen and C alphas. Okay, nitrogen, these are the broader peaks, broader pulses are the 180 pulses, the narrower ones are the 90-degree pulses. Okay, so these are the 180 pulses. All these broad ones are 180 pulses. They are applied with a certain phase. Now you have this T by 2 minus T1 by 2. So what is the total time period from here to here? It is T. So T1 by 2 cancels with the T1 by 2, and T by 2 plus T by 2, the total time is T. Therefore, it is called as a constant time experiment. So from here to here, it is a constant time T. In between, you introduce these various pulses, which will allow you to do an appropriate magnetization transfers. So the magnetization has come on proton as a nitrogen here. Okay, so I will explain that using the next. Okay, these are the, remember these various time points. Here, the time point is A, the time point B is here, time point C is here, time point D is here, then you have the time point E here at this point. Okay, you remember these time points there. So we will be writing the density operator for these time points. How the density operator looks at these time points. So A will be the time point of initial, this is the 0 point. Okay, this 0 point means the proton magnetization. This is amide proton. If the magnetization has to come here, which proton magnetization we are talking about? These are the NH protons. The C alphas will not come here. The C alphas cannot transfer to the nitrogen. When you are considering this, automatically all the other protons are filtered out. It is only the amide protons. Amide protons evolve and then get transferred to the nitrogen magnetization here at this point. Okay, what all happens during this period from here to here? Let us see that there. Okay, the flow of magnetization I've indicated to you in the summary. The flow of magnetization through the pulse sequence is like this. It starts with proton magnetization of amide. It transferred to the nitrogen of particular residue I. This is I and this is I. And here it is frequency labeled. T1 incrementation happens on this nitrogen chemical shift. Therefore, it is frequency labeled. And then from the nitrogen, it is transferred to the C alpha, as I indicated in the previous slide. Previous slide of 2 C alphas. Which 2 C alphas? The residue I and residue I minus 1. See, I showed here. This is the residue I minus 1 and this is the residue I. From the nitrogen, it is transferred to this and also to this. Okay, C alpha, I and I minus 1. And then you have T2 increment there. The time is incremented in T2. You therefore frequency label the C alphas. And then from the C alphas, it is transferred back to the nitrogen. From the nitrogen, it is transferred back to the proton, amide proton, and is detected here in T3. Okay, now I've written this explicitly in these ones. It starts with the proton magnetization HZ, and the evolution of this magnetization through the pulse sequence can be calculated using product operator formalism. At time point A, after the first inept transfer from amide proton to nitrogen along the backbone, the density operator is given by, this is the rho A is minus 2HIZ N Ny. So this is nitrogen magnetization, Y component nitrogen magnetization, which is antiphase with respect to the proton, right? Because it is the IZ here and IY there, and these are both of residue I. So HIZ refers to Z magnetization of the amide proton, of the ith residue along the polypeptide chain. And NIY refers to the Y component of the backbone and 15 spin of the ith residue. Thus, this operator represents the antiphase nitrogen magnetization with respect to the amide proton HIN. Okay. So, only relevant portions of the density operators are given. Other terms are not considered. So, because the total transfer has happened here from proton to the nitrogen. Okay. Following this, from time point A, the nitrogen magnetization evolves for a constant time period T under different Hamiltonians as below. What all things happen? First of all, the nitrogen magnetization evolves under the chemical shift for a period T1. During the period T1, there is a nitrogen evolution, chemical shift evolution of nitrogen happens. Then the proton-nitrogen coupling is effectively not there. Proton-nitrogen coupling, the antiphase magnetization was there. It does not evolve under the nitrogen-proton coupling and remains antiphase with respect to the proton. And which was, remember, it was antiphase here. Nitrogen magnetization is antiphase with respect to the proton, and it remains so. It remains so till the end of this constant time period. Okay. Then it evolves under the influence of one bond nitrogen C alpha coupling and two bond nitrogen C alpha couplings for the period T. Okay. So how does that happen? See, during this period, consider here we have T1 half, you take T1 T by 2 minus T1 by 2. We have simultaneous pulses on nitrogen and C alpha. Okay, simultaneous 180 pulses on nitrogen and C alpha. And therefore, that coupling is not refocused. So it will evolve under that coupling. And from T1 by 2 to another T1 by 2 from here, there is no pulse on the nitrogen or on the C alpha. Therefore, it evolves under that coupling as well. Therefore, for the total period, this one here, you have the NiC alpha I and two bond NiC alpha I as a coupling for the period T. Then evolution under nitrogen's carbonyl coupling is removed by the application of 180 band selective pulse to the carbonyl spins and also to nitrogen. See here, we have a 180 pulse applied here and in the middle. So this one will decouple the nitrogen carbonyl coupling, that is decoupled at some point, and at another point this pulse also serves the same purpose. So therefore, you will have the nitrogen C alpha carbonyl coupling is removed by the application of the 180 band selective pulse to the carbonyl spins and also to the nitrogen. Okay, so and during the period T1 half pi CO T1 half, decoupling happens due to the 180 pulse on the carbonyl spins. That is why I explained to you earlier. During the next period, T by 2 minus T1 by 2 minus pi, this is a 180 degree pulse on the nitrogen, T by 2 minus T1. So this is again a spin echo sequence here. See, this period and this period are the same. In the middle, we are putting the 180 pulse, and therefore this spin echo removes the proton and the nitrogen 15 carbonyl coupling. Because at this point, we are applying a pulse only onto the nitrogen and not onto the carbonyl. Therefore, during this period, the pi pulse on the carbonyl removes the coupling, and during the following period, this pi pulse removes the pi carbonyl coupling. Therefore, effectively, in the entire constant time period, there is no evolution under nitrogen carbonyl coupling. Thus, at time point B, the density operator is given by only the results are given here, remember. So only the results of the extensive calculations are given here, which are sufficient to understand how the pulse sequence has been working. So the row B, this is the time point B, the magnetization looks like this. For HIZ on nitrogen, amide proton, this then stands for the amide proton, and NIX, this is the nitrogen IX of the residue I, and the C alpha and IZ, this is the Z of C alpha of residue I. This is IZ, that means the Z magnetization of residue I of this amide proton, and this is the X magnetization of nitrogen of residue I, and this is the C alpha Z magnetization of residue I. And this is the coefficient which will come as a result of the calculations. Okay, this is time dependent. This will be dependent on the time. These are time dependent functions. Okay, and that will depend upon what is the time variable, constant time t. Okay, so now this is one term. The second term is exactly the same as this, except that you have here C alpha of I minus 1, because the transfer took place from the nitrogen of I to both C alpha and to C alpha of I minus 1, and that shows up here. You see, in either case, you have the nitrogen magnetization, which is antiphase with respect to the two C alphas, and also to the amide proton. So this nitrogen magnetization is antiphase. This term tells me this is nitrogen magnetization is antiphase with respect to the amide proton and the C alpha of the same residue. And this one tells me that the amide nitrogen magnetization is antiphase with respect to the amide proton of I and C alpha of I minus 1. And of course, you have the cosine. This comes because of the chemical shift evolution of the nitrogen. Chemical shift cosine omega Ni T1. So otherwise, you would not get the nitrogen frequency. So therefore, you have the cosine omega Ni T1. This will give you the nitrogen frequency. Okay. The first term represents the nitrogen 15 magnetization of ith residue, antiphase with respect to the amide proton, and C alpha of ith residue. The second term represents N15 magnetization of ith residue, antiphase with respect to the amide proton of ith residue, and C alpha of I minus 1 residue. Thus, a sequential correlation between I and I minus 1 residues is created. Okay. Following the application of pair of 90-degree pulses to nitrogen and C alpha at the end of the T period results in the density operator at time point C. So what happens here? Let's go back there. And this is, we are talking about these pulses here. These pulses, actually, if you look at from here to here this way, it is then kind of a transfer pathway from nitrogen to C alpha. Okay, so this, if you did not have this, it is like then inept here, right? So you have total from here to here, it is a transfer pathway from nitrogen to C alpha. So at this time point C, the magnetization is transferred from nitrogen to C alpha. Okay, so following the application of pair of 90-degree pulses to nitrogen 15 and C alpha spins at the end of the T period results in the density operator and time point C, which is like this. Now you see here the first term there gives rise to this one, the second term gives rise to this. What are these? These both represent C alpha magnetization because there is a transfer here. C alpha Y here and C alpha Y there. Okay, these are Y. So the Y means it is the transverse magnetization of C alpha. And now they are antiphase with respect to both amide proton and nitrogen because these are HIZ and NIZ. They are antiphase with respect to here, and here also this one is antiphase with respect to these two. And this portion remains the same, but of course you get these coefficients as they are in the previous. These are time dependent. This will depend upon the value of T. Okay. So now the magnetization is on C alpha of I and I minus 1 residues. See, this is the C alpha I minus magnetization of I minus 1. This is the C alpha magnetization of I residue. This magnetization evolves for the T2 period under the influence of C alpha chemical shifts. C alpha chemical shifts will evolve now. All the coupling evolutions except C alpha C beta couplings are eliminated by simultaneous 180 pulses on carbonyl, nitrogen 15 and proton channels. Okay, at the end of the T2 evolution at time point D, okay, now what are these? All the couplings evolutions are removed. Let me show you that. See here, we are applying 180 pulses in the middle of the T2 period here, and here. Therefore, all couplings, the magnetization is on C alpha. C alpha coupling to carbonyl, C alpha coupling to nitrogen, C alpha coupling to proton. All are removed. Therefore, it only chemical shift evolution of C alpha. So, at the end of the T2 evolution at time point D, the relevant density operator is given Y. So you have this rho D is equal to 4 HIZ NIZ C alpha I, C alpha IY cosine omega C alpha T2. How does this come from? This comes because of chemical shift evolution under T2. Other things are the same. And similarly, the second one also gives me the same. cosine omega C alpha I minus 1 T2, because this is the chemical shift is on C alpha I minus 1. It goes with that chemical shift. C alpha I minus 1 T2, rho 2 T. And cosine omega Ni T1 remains, except now this one particular coupling constant appears. And this is the cosine J C alpha C beta. This coupling constant cannot be removed. We remove the coupling to the carbonyl, remove the coupling to the nitrogen 15, and remove the coupling to the proton. But you cannot remove the coupling to the C beta because it appears in the same chemical shift region, and that cannot be removed, and that remains here. It remains as cosine pi J C alpha C beta T2. This magnetization is then transferred back to the coupled nitrogen spins by the simultaneous application of 90-degree pulses on C alpha and nitrogen. So let me go back there and show you these two pulses there. These two pulses, they transfer the magnetization back to nitrogen 15. Here it is on 15. And let me explain to you further that from nitrogen 15, from here to here, this C alpha coupling constant is refocused, and the magnetization therefore remains antiphase with respect to the proton at this point, and the nitrogen magnetization is then transferred by these pair of pulses to the proton, to the amide protons here, and from the amide protons it is refocused, and you collect the data here as this, and then you can decouple the nitrogen. So the same thing is read over there. A pair of the nitrogen magnetism, which is anti-C alpha, and also then evolves for the constant period T to refocus the antiphase character with respect to the C alpha. At the end of the T period, we have nitrogen magnetization, which is antiphase with respect to the coupled amide protons. Okay, a pair of 90-degree pulses on nitrogen 15 and amide protons at this point transfer the magnetization to amide protons. This proton magnetization is antiphase with respect to the nitrogen, and during the next inept block gets refocused to produce in-phase amide proton magnetization. The relevant density operator at this point is given by this. You have HIX cosine omega C alpha T2 gamma 1 T plus cosine omega C alpha minus 1 T2 gamma 2 T and cosine omega N T1. You see, all the other nitrogen and all product operators are gone. What has remained is only the proton operator there, amide proton operator there, and other things are simply as a function of T2. So frequency labeling of T2 has happened here, and frequency labeling of T1 has happened here. This T1 frequency labeling uses the nitrogen frequencies, and T2 frequency labeling uses the C alpha frequencies. This proton magnetization is then detected during the time T3, while N15 is decoupled in a broadband fashion. Thus, the resulting three-dimensional spectrum can be represented as S, T1, T2, T3, 3D Fourier transformation signal. F1 is N15, F2 is C alpha, F3 is amide proton. See, look at the pathway, how it has come. And this is the schematic of this spectrum there. So F3 is amide proton, F1 is nitrogen 15, F2 is C alpha. And if I take a cross section at one particular, let's take a cross section of this green one there. At what that I take the N15, this is the N15 chemical shift of the green one there. Okay, so at this point I take a cross section. At this cross I take a strip there, that is a strip. Okay, so only these two peaks are present here. So I take this small strip along this, F3, F2 strip, F3, F2 strip, add the F1 chemical shift of this. So I will have only these two peaks there, right? And what do these peaks tell me? This at the amide proton of residue I, it is showing me the C alpha chemical shift of residue I and the C alpha chemical shift of residue I minus 1 at the F1 of F1 N15 of residue I. Okay, so this is the sequential correlation. So you can go through this and stepwise, then you can actually walk through the polypeptide chain in a stepwise manner. And that is the beauty of this experiment. And I show you here. F1, the various nitrogen 15 planes, through the various nitrogen 15 planes. Okay, which are we are seeing here? How many nitrogen 15 planes we have to consider here? See, the green, the brown, the blue, and the red. There are 4 nitrogen 15 planes. Okay, this is at various places here. Okay. So you take these individual strips One strip here, one strip there, one strip there, one strip there. Like that, when you take the 4 strips, typically what you get the sequential correlations. If the F1 N15 of residue I get 2 peaks of residue I get a peak to the C alpha of residue I minus 1 and the C alpha of residue, C alpha of residue I and C alpha of residue I minus 1. Now if I go to the nitrogen 15 plane of I minus 1 residue, what I should get? I should get at the NH proton of residue I minus 1, I should get the N15 of C alpha of residue I minus 1. C alpha of I minus 1 I should get, and C alpha of I minus 2. And this C alpha of I minus 1 should be the same as this, because the C alpha is the same. This is I minus 1 C alpha. This is also I minus 1 C alpha. But this one is appearing as a sequential peak in the plane of residue I. This is appearing as a self peak in the plane of I minus 1. So this is the self peak. F1 is I minus 1 and the amide proton is I minus 1. So therefore this is the self peak. It is showing a C alpha of I minus 1 as the self peak. Now it shows a sequential peak to I minus 2. Now I go to the N15 of I minus 2. So now this sequential peak becomes the self peak here. So I minus 2, I get this self peak. I get a sequential peak to I minus 3. So I go now to the sequence, the plane of nitrogen 15 plane of I minus 3. So I get the self peak of I minus 3 and the sequential peak of I minus 4. Then you can go on like that. So therefore, we can walk through the polypeptide chain in a sequential manner. From one residue to another residue, you have connections. And there is no chance of missing anything here, because you're all based on 1 bond and 2 bond couplings. And these ones don't change too much. And therefore, this always peaks will be present. However, I notice one thing, that this intensity, the self peak, has a higher intensity compared to the sequential peak, because the sequential coupling constant is about 4 to 9 hertz. This is self peak is based on 7 to 11 hertz. Therefore, there is a small variation in this coupling that results in this different intensities of the peaks here. This also shows up in these coefficients, and these various coefficients which are present here, this one and this one. These are the coefficients which will actually dictate the intensities of the peaks. This is the intensity of the sequential peak, and this will be dictates the intensity of the self peak. So therefore, these ones will be slightly different, and that is, you can see that in the spectrum as well. So you will see different spectra in this manner. Therefore, you can walk along the polypeptide chain rather easily without any difficulty at all. And you have made use of 3 chemical shifts: amide chemical shifts, nitrogen chemical shifts, and the proton chemical shifts. And all of these are extremely useful. I think we probably end here. Unless there are any questions, I've tried to explain it, of course, in a very qualitative manner. The product operator calculations of these ones can be quite lengthy, but I have taken the important features of those, showed you only those particular relevant operator terms, which is sufficient to explain the transfer process of the magnetization and give the information content in the 3-dimensional spectrum.
You can ask them doubts, doubt clearance.
No doubts.
Experts they have covered too.
Huh?
You have completed today.
Yeah. So much of this what has to be done. See, the next lecture, I will do a little bit of this phase cycling and field gradients. I will take probably next time. Probably I will take 1 lecture. 2 hours not required. This one is slightly delayed. I'll take 1 lecture next time. That should be enough. And then after that, what do you want me to do? That will complete my dedicated
This part, my main course part.
So
then we plan some of the practical type of things, means some examples which they can solve, or you can show how to solve the spectra.
Yeah, so I have tried to go through that here, that detailed analysis of the spectra which are there. That is, I will show some spectra of peptides and proteins. I can show some spectra of nucleic acids.
So that way, maybe
So one of the small
one
molecules.
or two classes.
Maybe 1 or 2 classes.
2 days you can spend.
Uh,
Just think of how you can see no better, no?
Yeah, but it cannot be such an organized one, those ones.
Naturally not.
It will not be. So they take the spectra and then of course we have to analyze it one by one.
Yeah.
That is systematically one can do that. There is one other thing which I wanted to use. Of course, I will give one, I don't know if anybody covered, dynamic aspects of NMR. Dynamics in NMR.
Dynamics, but no.
So I will cover that. I will take one lecture on that.
Next one.
You see what is 16? Lecture number 16. You copied 16, no?
Yes.
16 is, I think, that is phase cycling in field gradients. Correct. Yeah, phase cycling gradient enhanced NMR. So I will take one, this one I will take. And after that, I can take some examples. 1 or 2 examples I will take of the spectra, analysis of the spectra. Actually, those great analysis of organic molecules, actually, Dr. Ghosh can do in greater detail, I guess. That is, well, I will show some spectra of the peptides, how to analyze peptide spectra, I will show. How to analyze spectra of nucleic acids, I will show in the next 2 lectures.
So we have next lecture on Friday.
Friday.
And Wednesday, I kept regular schedule.
Yeah.
And one lecture I kept as a reserve type. So we can use the next Friday also.
Yeah. We will see. May not, after the end of this month, I will not be available.
This month only, this Friday. And next Friday also I kept a reserve.
Reserve, okay.
Reserve for you. If required, you can utilize that. If not required, it's all in.
It's right. Yeah. So this is how many slides you can take? See that, go through this. See how many slides are there. This also has about
16. Yes.
16, how many? 20 slides. But it's a little bit tricky. To explain that, 20 slides is enough for one lecture there. But this is explaining gradient enhanced. Gradient spectral people are not familiar. What are gradients and all of that? I have to explain that. So that I will do. Next class I will do. And I have one lecture on dynamics. Dynamics in NMR. Dynamics is intrinsic to NMR. I think I should take that also. This is very fundamental.
Right.
That is very fundamental to NMR. I think that will be my next lecture, 17. 17 lecture can be dynamics in NMR. Then I will take 18, lecture number 18 will be trying to analyze some spectrum. 18 and possibly 19.
So that means Friday will cover this part.
Yeah.
Then next Wednesday will cover
next Wednesday the dynamics part.
And then next Friday we will.
Yeah. This coming Friday there will be 2 lectures, no?
Yeah.
Perhaps 2 lectures. So I will cover this part and also some portion of the dynamics.
You can finish that part.
You can finish that. Okay,
fine then. So every day 2 hours is there for us.
2 hours.
Whatever we need accordingly we can use.
Yeah.
Okay then. Okay, close.
Okay.
Students, so our class closed already.